Hello everyone, my name is Chunyoung Jung at University of Illinois. Today I'll be presenting extratropically transitioning theses and their changes under the warmed environment in the future in North Atlantic Basin. This presentation focuses on landfalling cases. Let me start with the reasons why I am interested in these events. These systems can impact densely populated areas far removed from the original TC event. Beyond their immediate vicinity, they could affect weather conditions farther downstream, for example, Western European countries. Then will climate warming alter the ET process? Well, it's not clear to answer the question because we have both favorable and unfavorable or unclear conditions coexist projected in the future, according to the previous studies listed in these boxes. So far, there is no concrete conclusion about which will be larger in the future. So the goal of this study is to examine how the dynamics and impacts of TCs undergoing ET and their interaction with middle-latitude Rossby wave packets will be affected by climate change in the North Atlantic Basin. Let's move on to the method. To get more robust conclusion, we needed as many cases as possible. So we collected North Atlantic ET cases over 40 years from 1979 to 2018. We used HERT-2 for TC information and ERA reanalysis for gridded data. Then we classified ET cases into three types according to their tracks, which are straight-moving, recurving landfall, and recurving ocean, as illustrated in this figure. This is a very straightforward way to classify. We only used latitudinal and longitudinal threshold to categorize them. For example, straight-moving cases were classified if the storm did not cross 20 degrees of latitude until crossing 80 degrees of longitude. In this presentation, we focus on RCL cases. We can get several benefits from this classification. First, we can group the ET cases into cases with similar synoptic patterns. Second, we can consider potential impact of climate variabilities, such as ENSO, by using track-based classification. This way of classification results in total 37 RCL ET cases. I took step forward to narrow down the number of cases based on the study of Evans and Hart 2003, and I ended up choosing 15 cases randomly out of 21 cases to form a small ensemble with varying composite initial conditions. This is a preliminary result, so in this presentation, the results from only one ensemble member are shown. To composite the selected 15 cases, I re-coordinated every cases relative to the storm center and composited environmental fields which are used as initial and lateral boundary conditions of simulations. For the future simulations, pseudo-global warming procedure was employed. PGW is a way to reconstruct climatological projection by adding a climate difference between future climate and historical climate to current atmospheric state, which is reanalysis data. Then we can get new reanalysis data, which is under the projected climatologically warmed environment. To look into ET process, defining ET onset and completion is important process. The cyclone phase space proposed by Hart et al. 2003 is widely used as a tool to define ET onset and completion. Here I basically used the CPS definition to define the onset of ET By comparing low atmospheric thickness between right side and left side relative to storm center and motion. On the other hand, the definition of ET completion of CPS didn't work in our simulation due to lingering warm core in the storm center. We used composite fields for initial and boundary conditions, which may weaken mid-latitude wave amplitude, resulting in the lingering warm core in transitioning storm at higher latitude. Since CPS ET completion is defined by the time when storm becomes cold core system, it failed to resolve the ET completion in our simulations. So here we devised a new way to define ET completion by employing two metrics representing TC energy sources, surface latent heat flux, and Bernoulli conversion in eddy kinetic energy equation. Through an examination with 10 ET cases, we defined ET completion as the time when the value of linear regression of Bernoulli conversion becomes larger by 100 watt per square meter than that of the latent heat flux. Bernoulli conversion can be derived from both eddy kinetic energy and eddy available potential energy equations, where this term is a source or sink term in the eddy kinetic energy budget. The diagnosed time by the new matrix was compared with satellite imagery, which is typically used for ET completion subjectively. These figures are example derived from RCL present-day simulation. Let's look at the leftmost figure, CPS diagram. The x-axis minus VLT represents whether the storm has cold core or warm core. Positive values indicate warm core and vice versa. The figure in the upper left panel presents CPS diagram for present-day ocean simulation, and you see the CPS does not resolve ET completion, while the storm shows typical appearance at the time of diagnosed ET completion by our new method shown in lower panel figures. The storm shows clear comma-shaped appearance and one frontal feature in the northeastern quadrant. Based on this, we applied this method for all simulations. Given the RCL storm's track, the RCL events potentially pose direct threats to densely populated mid-latitude regions along the US East Coast. In this regard, we designed a set of simulations consisting of 7 sensitivity simulations to test the role of topography to isolate the effect of TC and projected changes in volcanicity. Let's take a closer look at sensitivity simulations. To test the role of topography, we designed aquaplanet mode simulations called ocean simulation, in which all topography was removed and entirely covered by the ocean. Next, to separate effect of warming and projected changes in volcanicity on the event in the future, we set 2 different simulations. Left figure shows delta T between the future and present day for control simulations called future ocean simulation, where we see tropical tropospheric warming maximum and polar amplification at lower troposphere, which influence upper and lower level volcanicity. To separate the effect, we designed the uniform delta T simulation, in which the atmosphere is uniformly warmed vertically using vertical average of delta T, which means there's no changes in volcanicity in the future in this simulation. shown in the right figure. Lastly, we conducted no TC simulation, which is not shown in this poster, in which TC vertex was removed. This simulation is designed to see the role of TC on downstream Rossby wave development. Let's move on to results now. The results are derived by 4 different parts, including overview. First, take a look at the differences in track and minimum sea level pressure, which is intensity, the proxy over intensity for all simulation, except no TC simulation, of course. Left figures are derived from ocean-based and right figures from land-based simulation. Red lines for future, blue lines for present, and purples in the left figures depict uniform DT. Here, the time of ET onset is labeled ET small b, and ET completion is labeled ET small e. As you see, the tracks of future and present day one are quite similar each other, so we can make a direct comparison between them. In terms of ET duration, no significant changes are found between the future and present day simulations. For the intensity changes, noticeable features are as follows. Minimum sea level pressure is stronger in the future. All storms undergo re-intensification during ET phase, while future storms undergo weak re-intensification. Future uniform delta T storm undergoes relatively strong re-intensification. In addition, future uniform delta T shows strongest minimum sea level pressure among 5 storms. To clarify the cause of the difference, we conducted column-integrated eddy kinetic energy budget analysis, shown here. Here we focus on Bernoulli conversion term, second term in the right-hand side, which is a source term for eddy kinetic energy budget. These figures represent time series of Bernoulli conversion in dotted lines and surface latent heat flux in dashed lines. Red for future and blue for present. Let's look at the Bernoulli lines. The prominence difference of Bernoulli between future ocean, which is controlled run in the left figure, and future uniform delta T run in the right figure is found at late stage of simulation, marked in red circle here. Interestingly, while future ocean storm becomes weaker when it comes to Bernoulli conversion, future uniform delta T storm maintains its predominance in Bernoulli conversion until the end of the simulation. Given the energy source of extratropical cyclone, this allows the future uniform delta T storm undergoes strong re-intensification process compared to the storm in the control run. A possible explanation for the stronger Bernoulli conversion in the future uniform delta T is that lack of polar amplification hampers reduction of the available potential energy reservoir in contrast to the other future ocean and land simulations, facilitating the convergence of available potential energy to eddy available potential energy, and thus strengthening the re-intensification. Let's move on to the precipitation. This table represents temporally and spatially averaged changes of precipitation with regard to experiment TC phase and radius. Here I'm going to highlight lens simulations because we could assess the societal impacts associated with the transitioning TC-induced precipitation. Let's look at the land results first. As you see, Maximum precipitation rate is seen at inner core region during TC phase, while seen in mid-core 300-kilometer region. The region moves outward as the storm undergoes transition, which is typical characteristic of the transitioning storm. In addition, as expected, future storm shows a much stronger precipitation across the phases and ready, shown in red and blue boxes. Interesting thing is the rate of increase in precipitation during ET is much greater than that of in TC phase. And I also visualize precipitation changes here in the right figures. Lastly, downstream development. Here, the amplification of the downstream wave train is measured using amplitude of its associated eddy kinetic energy maxima. These figures are showing Hopf-Miller diagrams of a vertically averaged meridional wind in contours and eddy kinetic energy in shadings in the first column, Barockley conversion in contours in the second column, ageotropic geopotential flux divergence in warm contours in the third column. For present ocean in upper panels and for future ocean in lower panels. Let's look at the first column. Amplified eddy kinetic energy maxima are evident in the downstream of their future and corresponding increased meridional wind speed there. Second column indicates a stronger Barockley conversion in vicinity of the future storm, and it partly overlap EKE maximum vicinity of the storm. In addition, enhanced ageotropic geopotential flux convergence and divergence in the immediate downstream region shown in the right column. This implies that additionally more generated EKE associated with the future transitioning TC contributes to additional amplification of downstream EKE maximum through ageotropic geopotential flux divergence and convergence. The future uniform delta T and land TC showed similar features to the future ocean simulation, which are not shown here. To see the role of the transitioning TC on downstream development, I displayed EKE terms derived from no TC simulations. As you see, no significant downstream development is found in the future, second and fourth figures, unlike first and third figures, which confirms that the transitioning TC acts as an additional source of EKE, contributing to downstream development. I'll skip the summary and thank you for listening to my talk.